Okay, let's talk about hypothesis testing. So again, as a part of the overall research process, we start with a research question. We look at the data. We basically look at past literature to see what has been done, what theories are out there. And from those theories, what we're aiming for is a testable hypothesis. And a hypothesis is usually going to be basically termed in the term of construct. So we're not going to talk about a 5-page study guide involving 7 sections of 10 items each will improve the performance on a 50-item multiple choice test. That's too specific. That's operations. You're defining the methodology of the study. Hypothesis testing is going to be study aids in the form of guides can improve test performance. So we're at the construct level. It might be depression predicts violent behavior. So again, not what type of depression. It's a broad, it's in the land of theory. It's in the land of constructs. Now, hypothesis testing is an inferential procedure where we now look at the actual operations that we created to allow us to look at a quantitative inferential procedure. So we're going to use sample data to evaluate the credibility of a hypothesis about a population. So there's a lot in that sentence. So inferential, again, we're inferring. Now, inferential is not the same as causation. Inferential simply means that there is a pattern that I find in my sample that I can infer would likely also exist in a larger population. So again, inferential is about inferring from your sample to a larger population. It does not make a conclusion about whether it's causal. It simply says the pattern I found might be found elsewhere. And what we're going to do is we're going to test that hypothesis. We're going to look at a sample population and find out, do we find support that generally study guides affect test performance, or do we find a lack of support? And we're going to be testing a specific sample. If we find that pattern in the sample and that pattern is not likely due to chance, we then have to make the argument about how credible is that hypothesis being able to infer to the population. And again, a lot of that is about logic and methodology. So if I have a very tightly focused study, I'm looking at one type of study guide in one graduate class for, let's say, Statistics 520, and I'm looking to see, do those study guides improve test performance? I can find a reliable pattern. Now, what can I infer that to? Can I infer that to grade school students learning about history? Can I infer that to German students in Germany learning about German history? I don't know. It might be harder. I can probably reasonably infer that study guides would help other graduate stats classes. Now, let's take a look at that same study done a different way. So again, I'm interested in study guides, performance and test performance, but I've got more funding. I've got some colleagues willing to help out. So we actually introduce somewhat similar style study guides in all sorts of classes. We do some of them in other states. We do some of them in grade school, some of them in high school, some of them at graduate level. We do them in history classes. We do them in science classes. We do them in English classes. We do them in math classes. And we find across the board in all of those classes and all those settings, they work. Again, all I found is a pattern. Tests, study guides, improve test performance. But now, because of the methodology of the actual study, it is much more credible for me to actually infer that study guides would work in a wide variety of situations, that it would affect a greater population. We sometimes will use simply effect size estimates instead of hypothesis testing. We'll basically just look for the difference. So we won't have a hypothesis. We'll just do exploratory analysis and look for how big the patterns are. So basically, when we find an effect, what we're talking about is we're finding a mathematical difference in an outcome variable based on a predictor variable. So we have different levels or different values of an IV, and we find that those values have a predictive relationship with the outcome values. We can have statistical significance, we can have meaningful significance, and we can have absolute difference. And we want to talk about each one of those slightly differently. The gold standard in psychological science is statistical significance. And what statistical significance is simply a marker of how likely is the pattern that you found due to chance. You've probably all learned over and over again you need a p of 0.05 or lower. And all p is, it's a probability estimate. That's why it's p, probability. And what is the probability? The probability that your effect, that your pattern, was due to chance. So if the chance that your pattern would have occurred just due to random fluctuations is less than 5%, we say we have statistical significance. The problem with just statistical significance, though, is depending on your sample, depending on the statistics you're using, and depending on just how many people are in your study, sometimes some fairly small differences are statistically significant. So you also want to think about, especially for an applied setting, meaningfully significant. So for instance, if I do an intervention at a grade school that costs $1 million a year, and I find a statistical significant difference with the implementation of this $1 million a year program, but that difference is a change in a grade from an 80 to an 82 on average. Is that meaningfully significant? Is a 2-point increase worth that much money? That's the applied question we sometimes have to ask. So as scientists, we're just worried about whether or not it's statistically significant. That's our marker. But as practitioners, we want to ask also, what's the meaningfulness? What's the practical implication of these findings? What's the absolute difference? What is really going on? And sometimes you'll also find in studies when you're reading, if they report something as statistically insignificant, but still give you descriptive data, what they're basically saying is, it may be due to chance, but look at this absolute difference. A good example of this is a study that I'm very fond of that's actually in industrial organizational psychology, and it's looking at basically hiring procedures around stereotypes. And they actually found an insignificant difference in whether or not you got a callback based on kind of the stereotype groups that you were in. But the absolute difference was pretty staggering, because the statistic they were using was not a very sensitive statistic. It tends to underestimate whether or not there's actually a meaningful difference. And they reported the difference, and it was that one group, we'll call them the majority group in this study, 70% of them got a callback after the interview. The minority group, the group that was stereotypically in the minority in this particular study, only 40% of them got a callback. It was just, that difference sounds large. It's a meaningful difference. It's a big absolute difference. But the sample size was small enough that the statistics came back and said, not quite, p equals 0.07. But the absolute difference was very meaningful in that case. So just recognize that though we are going to focus on statistical significance because this is a graduate level statistics class, don't lose sight of it is not the end-all be-all of decision-making in applied organizations. So by the nature of hypothesis testing, when you have a hypothesis, you need to have it phrased in the form of either a null hypothesis or an alternative hypothesis. The null hypothesis is typically not stated, but it is the opposite of whatever you state. So any hypothesis needs to have an alternative that it's wrong. So, for example, study guides improve test performance. That's the alternative hypothesis. The unspoken null hypothesis is study guides have no relationship to performance. And the reason we need to focus on this is because of the language of hypothesis testing. It's built around this idea that every stated hypothesis, generally an alternate hypothesis, has an unstated null hypothesis. In other words, you have an equal chance of finding out you're wrong as you do that you're right. So again, another kind of general methodological model. So we generate a hypothesis, and the hypothesis itself needs to be testable. And basically, there's two alternatives then. There's the alternative hypothesis, the hypothesis we're testing, and the null hypothesis, the hypothesis that we're wrong. We then specify a significance level, and this is our type 1 error rate. The significance level typically in social psychology and psychology field in general, and in fact in most sciences, has been set for us. It's kind of a norm of 0.05. But that means that if you have a p of 0.05, there is a 5% chance that your findings are an error. That's type 1 error rate. You claim there's an effect that wasn't due to chance, when in reality it was due to chance. You were in that 1 in 20 chance where it just happened to be these two groups randomly were different from each other. So once you've actually set your significance level, generally 0.05, you're going to pick an appropriate sampling distribution. And you're also going to calculate how much of sample do you need to have power. So based on previous research, what is the likelihood of how big of a difference you're looking for? So if it is a big difference, if you're expecting study guides to change people from having C's to A's, you probably don't need a huge sample to find that effect. But if what you're looking for is a fairly small effect size, if what you're actually expecting is about a 5% increase, you may need a much larger sample size to find that difference. Why sample size is important is, basically speaking, the larger your sample size is, the more forgiving the statistic is to assuming that if you find a pattern, it's not due to chance. So then we're going to get our sample. We're either going to randomly compute it, we're going to collect a sample. It may be random, it may not be not, but we're going to get data. We're going to collect that data, and then we're going to run the statistics. We're then going to compute the probability. We're going to construct the p-value. We're going to look at the patterns and find out, is this pattern based on the size of our sample likely to have occurred due to chance or not? Then we take a look at that observed statistic, and the observed statistic is basically going to be, we need that observed statistic, the value you would calculate with the statistical technique, to be above the minimum required for the p-value we're looking for, in this case 0.05. If we find that, at that point, we can say that the alternative hypothesis was supported. So if our test statistic indicates a p-value less than 0.05, our alternative hypothesis is supported. It's not proven, it's not correct, it is simply supported. So in that point, we're going to reject the null hypothesis and claim support for our alternative hypothesis. But if that p-value is above 0.05, if it's greater than alpha, we have to accept the null hypothesis, that unspoken hypothesis that we were wrong. There was not an effect. So when we look at hypothesis testing, we're basically looking at the graph here at the bottom right. We're looking at the true state of affairs versus our decision. And again, we don't actually know the true state of affairs. The true state of affairs could be that HO, the null hypothesis, is true, or that HO, the null hypothesis, is false. What we do know is our statistical decision. So if we don't reject the null hypothesis, if we agree there was no findings, as long as there truly was no finding, we haven't committed error. But if there really was a pattern and we missed it, we've created a type 2 error. In other words, we're saying there isn't an effect when in reality there is. Now, for the most part, because we can't know the true state of affairs, we as a science have decided that we're okay with an inflated type 2 error rate. We're okay saying we didn't find it this time and we can't claim it, and we may be wrong, mainly because people will keep doing studies. They'll keep looking for the effect, and if it's there, they'll probably find it. But what we don't want to do is claim an effect when it isn't there. So we don't want to reject the null hypothesis, and rejecting the null hypothesis means that we have supported our hypothesis. We've said there's an effect. We've said there's a pattern, when in reality there isn't one, and that's a type 1 error. And that's why we've set alpha at a fairly low value, 0.05. We want to be 95% confident before we ever claim that we found something, because people may make decisions based on what we claim. And again, if we reject the null hypothesis, and indeed the null hypothesis was false, there was an effect, we have power. We've found the effect and there is an error. So generally speaking, when we're testing hypotheses, we can have two situations. We can have a one-tailed directional hypothesis or a two-tailed test. So my examples so far have actually been directional hypotheses. Study guides will improve test performance. So in a one-tailed test, basically, if I find there is no difference, or if test performance got worse, I've supported the null hypothesis. The only way I can support my hypothesis is I specifically have to find that the group of study guides did better. There is a different form of hypothesis, and that's the two-tailed test. That is a hypothesis that basically says there's a difference. Study guides will affect test performances. Now, the only way the null hypothesis is supported is if there really isn't either greater or worse performance, there is no difference. And any difference, either improvement or reduction in performance, is supporting the alternative hypothesis. Now, there's a reason both logically, methodologically, and statistically to do one-tailed tests. Methodologically, we actually want to be asking questions that there is a fair amount of information on already to where we can ask basically interesting questions. So finding out that study guides make test performance worse is actually not necessarily something you'd expect to find. So we want to word our hypotheses, if we can, directionally. The only time we'd ever try to do a two-tailed test is if we're studying something that truly hasn't been studied before and we really have no theory or past research to suggest. It might be a brand new substance and we have no idea if it's going to make a disease worse or better till we try it in a controlled setting. That might be a two-tailed test. So again, our type 1 error is when we make a claim of an effect when it isn't there, and it's based on p-value. And that p-value is trying to give us power and confidence to where when we claim an effect, we can be pretty confident it is there. But because we are so worried about making a type 1 error, making a claim of an effect when it isn't there, we have an over tendency to actually make type 2 errors in our research, missing effects that may indeed be there. Now I want to get into a little bit of the statistical reason to go with the one-tailed test. So power, your chance to find an effect if it's actually there, is influenced by 4 different things. The first one is sample size. The larger your sample size, the more people in your study, generally speaking, the smaller an effect that your study will find is significance. And again, this is because our statistical significance, our estimate of probability, our p-value, is an estimate of how confident can you be that your sample would infer to a larger population, which means it's been adjusted for sample size. The larger your sample, the more confident you can be that what you found in your sample would be found in your population because you got more of your population in your sample. The second thing is effect size. So how big of an effect is it? You can usually affect this with methodological questions. So again, if I was looking at a very simple test, looking at the effects of music on test performance, if I was comparing the differences between Miley Cyrus and Lady Gaga, I would not really expect there to be a vast difference in their music. Now, if you're a fan of one or the other, I'm sure you can tell me there is differences, and indeed there are. There's differences in subject matter of the song. There's a little bit of a difference in the complexity. There's also a little difference in who's actually writing the songs and also performing the instruments. But overall, they're similar music in a similar style. So I would expect that effect size to be fairly small, even if music does predict performance. But if what I'm interested in is looking to see does music affect performance, I could increase the effect size by choosing 2 very different styles of music. I might choose soft spa music versus heavy metal. I might compare Zanfir, the master of the pan flute, and some of his music to Slayer. Now, I'm probably going to find if there is a difference in music, those are 2 vastly different styles of music, which means I'm more likely to find a larger effect because of the difference. So that's how we use methodology to increase power. We could change our type 1 error rate. We could change alpha. Generally speaking, this really just isn't socially allowed, if you will. But it is one of the things you can affect. If you're willing to accept a greater type 1 error rate, in other words, you accept a p-value of 10% or less, so a 10% chance of being wrong, you'll also have a greater chance to find differences. And the final way we can increase power is that a one-tailed test is more powerful. So one-tailed tests, generally speaking, require a smaller absolute difference for our statistical technique to say this is a meaningful difference than a two-tailed test. And what this really comes down to is that in a one-tailed test, we're accepting a 5% chance of being wrong. But that 5% chance of being wrong is directional. In other words, the only way that I'm wrong is if it is specifically test performance underperformed. In other words, I'm looking for test performance to improve, which means all of my error is in one direction. So that 5% chance of error, I'm only looking at one tail of the distribution of performance. If I'm looking at a two-tailed test, I have to split that alpha. I'm now looking for either under or over performance as a potential cause or a potential statistical pattern I'm interested in. So I'm interested in both. Now I only have 5% chance of error that I can spread, so now I have to cut it in half. I basically have to find a bigger difference either going above or below the score that I'm looking at. And I'm going to walk through this in a couple other examples to hopefully kind of get you to understand this idea. So what we're talking about here is now the mathematical statistical reality of a one versus a two-tailed test. So again, test statistic probability distribution. Whenever we're actually comparing a difference, and I think, this is something you've got to get your mind around a little bit, that at the most simple of levels, if we're doing a t-test comparison, we have an independent variable with two levels, study guide or not, and we have an outcome, test performance. When we run our sample, we're going to find a difference, hopefully, between those with study guides and those without. And that is the result of our one study. Let's say that difference is 15 points. So the people with study guides scored a 70, the people without study guides scored a 55. So there was a 15-point improvement with the study guides in my sample. What our statistics ask is that 15-point increase, how likely could that have occurred due to chance? In other words, if I took hundreds of samples, let's say my sample was 50 people. If I actually ran that study over and over and over again, every single time I grabbed 50 people, and every time I randomly assigned people into group 1 or group 2, but no one got study guides. So I did no intervention. I just split them into two groups. How often would I find a 15-point difference between the two groups when I didn't do anything? And if I find that 1 out of 20 times I find a difference of 15 points or greater, that means I did not hit my significance probability of a p of 0.05. So how we're looking at that is once we have our test score, our obtained test score, what we're actually comparing it to is a theoretical distributions of how likely, based on the sample size that we had, is that difference going to occur due to chance and not intervention. Now, if we have a one-tailed test, basically all 5% of the values that I'm looking at are high scores. I'm looking for improvement. So basically, if the magic number is 14 or higher, is less than 5%, then any score above 14 in the direction I'm predicting, improvement, means I found statistical significance. So that critical value is based, again, on the distribution we're looking at in this slide is not the distribution of our sample. It is the distribution of any possible combination of samples of the size that we drew. And how likely is the difference that we found in our sample to occur if we ran that study hundreds, if not thousands of times with hundreds, if not thousands of samples. When we move to a two-tailed test, we're still comparing the difference, but now instead of plus or minus 15, instead of just plus 15, I also have to accept that if it's minus 15, it's also significant because I'm willing to look for both an improvement or a decrease in the score to support my two-tailed hypothesis. I'm just expecting a difference in either direction. So now in that possibility distribution, I have to find a higher value, either positive or negative, for me to claim that there's only a 5% chance, because I'm having to split that 5% chance to the upper and lower possibilities of all distributions. So again, that's why a one-tailed test is more powerful than a two-tailed test. So let's walk through what's actually happening with an inferential statistic. With an inferential statistic, we start with a population. And we often refer to the population as mu, which is an actual Latin symbol representing population. So the population is whoever we're wanting to infer to. If I'm trying to do a study in a single classroom and all I'm inferring to is SIUE, then my population is all students at SIUE. If I'm trying to just infer to people within the United States ages 20 to 40, that's my population. If I'm trying to infer to all human behavior, my population becomes the entire world. So a lot of times we need to know and define what is the population we're wanting to infer to. Once we've identified that population, we want to use some methodology to get a sample of that population. The better you do this, the more likely that you actually make sure your sample is actually randomly drawn from the population, often not possible. But if you can do random sampling, you will have an easier argument inferring back to the population later. Most of the time we do what is called convenient sampling. So if I'm interested in college students, guess what? I'm probably going to use SIUE college students. That's not a random sample, that's a convenient sample. Once I have my sample, whatever difference I find in my sample isn't mu, it's mean. It's the mean difference. It's the absolute difference that I found within my study and my sample. So I have a sample of 50 with a known effect. I run my study, I find an absolute difference, and I'm going to look at the statistical reality of that difference. I'm going to look at the effect size. How big is the difference between group 1 and group 2 in their test performance? And I'm going to then compare that to the population estimate of all possible samples of 50 without an effect. How often would we find just random fluctuations between groups in the population of the sample? So that's basically going to create my estimate of the population and the likelihood of any one particular effect being found. Once I've done that, then using my p-value, I'm going to identify within that range of possibility at what point is a known difference big enough that it's only likely to occur due to chance 95% or less of the time, or more of the time. Sorry, more. So once I've done that, again, if it's a directional hypothesis, it's going to be a 5% on whichever direction that I've hypothesized. If it's non-directional, it's going to be 2.5% on either side, reducing my power, requiring a bigger difference for me to claim statistical significance. So once I figure that out, I'm going to actually calculate my test statistic. I'm going to calculate what is the test statistic. In this case, for example, t. I'm going to take the mean of one group minus the mean of the second group and divide it by the variance total within the group. And don't worry about these numbers right now. It's just the mathematical equation that we're going to use to generate a test statistic. We're going to get a value. Now on the other side of this equation, I'm going to use a probability table. And it's based on the probability of error, p, the size of the sample, and whether it's a one or two-tailed test. And again, what I'm going to be doing is looking to see the size of my sample, what is the test statistic I would have to find or greater for me to be confident that it's 95% or greater chance that that occurred due to a real pattern and not chance. So that's going to generate a critical value. And the critical value is going to be coming from, again, the sample, whether I've done a one or two-tailed test, and what p-value I'm looking for. If my test statistic is above that critical value, I have statistical significance. Now just recognize that within this big model, there's also the fact that every time we therefore run a statistical test, we're effectively coming up with a single probability. It's like flipping a coin, but it's a weird multidimensional coin. And every time we flip it, there's a 95% chance we end up on the right side of the coin. We claim an effect, and it is there. But there's a 5% chance we get the weird small side of the coin, where we claim an effect and it isn't there. But that probability, that estimate, is based on a single test being ran within your data. If you ran a second test with your data, exact same data, and ran another test, that test also would give you the information of a 95% chance of being right with a 5% chance of being wrong. But you've now flipped the coin twice. Your chance of one of those coins being wrong is now above 5%. So recognize that because we are basically trying to estimate the probability of whether we are making a true claim or not making a true claim, we also have to be aware that running multiple tests on the same data, our statistics don't know that we're running multiple tests. And if I ran 5 tests on the data and every single time I got a p-value of, let's say, 0.04 or 0.05, the overall chance that every one of those was correct is actually greater than 0.05. And we'll talk a little bit about ways to adjust this as we move through the class. So the effect does not change, but now the estimate overall across all tests in your sample, your estimate of probability is being underestimated. There's a greater chance that at least one of your results is actually incorrect when it's claiming correct, and you can no longer claim that across all of your tests you only have a 5% chance of being wrong. You have a 5% chance of being wrong in each individual test. Collectively, you may have a greater chance of being wrong somewhere.